I mean, no.
Yeah, it was started out with the phone, but like off the camera shop. So it was over there. I need to do that.
Forget that door right over there. I consider like.
Huh? I'll put it on the quiz. Woo!
What?
That moment when you spent
Like, I make everyone write their own birthdays down so you don't do it later.
Have you ever seen
And you make everyone write their own address in the envelope so you have to do it later.
Have you ever seen the movie Why Him?
I just got moved down here for that.
You got a what?
Have you seen the movie Why Him?
No.
God, it's so good. Okay, it's basically what if your parents just met your boyfriend and then he wasn't very social.
My nemesis, like here.
Okay, so they're at dinner and he's like,
Oh my god,
Guys, so guys, real quick. That's what I got for number one. And then you look a little further down the page and you realize the answer is actually just staring you in the face already. What that shit? Just this table I found in an old book, it just rounded to 3 places. What do you think 0 plus means?
Close to zero, but not.
Close to 0 but not 0.
Basically negligible.
Like 0004 or less. That's where they would call 0 plus. So, but probably at least one head. What does at least one head leave out? No heads. I like it. So the opposite is no heads. So if I do 1 minus the probability of no heads, 14 choose 0, 0.5 to the 0, 0.5 to the 14. So if I do 1 minus, just to cut to the chase, 0.5 to the 14, you get a 999. Rounding to 4 places.
We could also just do like 1 minus 0.5 to 14.
That's what I did. Because how many ways is there to choose nothing from 14? 1. I don't choose anything. So that's 1. What's anything to the 0 power? 1. So happy. Anything to the 0 power is 1. So the only thing that's there really is 0.5 to the 14. Okay. This little middle part is if you want to know how to use the calculator to check your work. There's another way to do it. If you don't want to know how to do this, then just don't worry about it. I love it. Here's the mean formula, right? So obviously, if I'm going to flip a coin 14 times, how many heads do I expect? 7. And sure enough, 14 times 0.5 is 7. And then the standard deviation.
I say keep one.
What do you guys get?
What'd you say?
I say keep one to myself.
Hell no.
Then you get
What
1.871.
I mean is that you judge people.
All right, how are we doing so far?
More of a life
I'm an open book.
What is it?
Ask me anything. I'll tell you the straight answer.
Do math for fun.
1.871.
Oh, yeah.
So standard deviation, you round to at least 3 places. If you want to make a blanket thing, so you have to remember when to do what. You can take everything to 4 places, right? And you're golden. I just don't want to see 18 places, and I don't want to see 1 place. It's not enough, and that's too much. Those 2 things. Okay. So now this kind of new idea, the minimum expected number of heads. U minus 2 sigma. So I do 7 minus twice 1.871. And what do I get? 3.26 roughly. And I'm going to do U plus 2 sigma.
10.742.
10.74. So if I flipped the coin, if I flipped the coin 14 times and I got 12 heads, would that be unusual? Officially, yes. I like it. So it's very weak evidence, but it's possible evidence that it's been tampered with. The larger the number of trials you do, the more evidence it shows when it's unusual. Right? Okay. How are we doing so far? That's kind of old news. I'm trying to marry the stuff we know with what we're about to get into. And that's legal now. So now, what I've done is I've taken all of the possibilities. I actually just stole this out of an old textbook. But if you use the formula on every possible value of x, 0 through 14, rounded in 3 places just because that's what they did in the book, you get those values. Is that, you guys with me? So that's like an x, p of x table. So that x, p of x stuff, the p of x could be any probability way. I could make a table that shows all the values for a binomial situation, and now it's an x, p of x deal. And then I can graph it. I can make a little histogram out of it. All right, so how wide is each of these bars?
1.
1. From 7.5 to 8.5 is 1. So the probability of 8 ends up being equal to the area of the rectangle that represents 8. So when anybody play darts? Anybody?
Yeah.
Yeah? Okay. Especially when you're drunk and you have a nice, they set it up correctly so you can't hurt anybody. That's nice.
Steel tip or soft tip?
I should show you, I show my algebra students a video of somebody who engineered a dartboard that will always, you'll always get a bullseye. Have you seen?
Wait, I need to learn this.
Huh?
Mark Roberts, engineer that built it.
Yeah, so it goes into the equations behind it. It's kind of cool, right? Anyway, that's for algebra. I like to show that because it goes into y-intercept and all kind of business. So anytime you represent a probability distribution visually, if I graph a probability distribution, the area related to a question I have is equal to the probability of that. So on a dartboard, why is the bullseye given such a high value? Because it's such a small area. It's hard to do that by chance. What's the probability you hit it in that little area? It's related to the area of that bullseye related to the whole thing. So maybe the bullseye is like 5% of the whole area. I don't know. So there's a 5% chance you would just randomly hit that if you hit the board. Are you guys? That's why it's given such a high value, because it's a hard place to hit. You like it? Maybe? You guys, anybody not know darts at all? I'm sorry.
Well, you got 25 and you got 50.
All right, you can look it up. Okay. So the probability of at most 6. I tried to give you a physical example to remember what at most means. You could be at most 12 to eat off the kids' menu at Denny's. You can have at most 6 people in an elevator. So when that seventh person tries to step on, you're like, yeah, are you crazy?
Trying to kill us all.
So at most 6 people in an elevator, the 7th person might kill you. And you're like, get out of here. Okay. As we all grow, we have to kind of decrease that number. But so how do I get that answer? Just from the picture or from the table? At most 6 means 0 to 6. So what's at most 6? At most 6 is 0, or 1, or means add. So you just add the damn things up. What do you guys get? 395. I like it.
My hair's on that.
Of course not. Why would you?
Why
Why would you do 1 minus that? Did we calculate the opposite of my question?
You would have done me straight for the last time.
Oh, wow. It got serious over here.
Dang.
Sound like there's going to be a duel. All right, if you're going to duel somebody else, you have to do it outside. All right? You can slap them in the face with a glove, and then you take it outside. Guys, hey, everybody. No duels happening. Don't look over there. It's okay. Calm down. So why would I not do 1 minus that? Did we calculate the opposite of what that thing is asking me? No, we didn't. So why would I do 1 minus that? At most 6 is 0 or 1 or 2 or 3. So when I add those up, that's the answer. If you added up 7 through 14, then you better do 1 minus that. But why the hell would you do that? That's just as much work. It's actually more work. Yeah. So you're trying to generalize something. What did I say? When do you do 1 minus? When do you figure out the opposite and do 1 minus? When the opposite has a lot less work involved. Here, doing that is at least is a little less work than doing the other way. So screw the other way. I'm just going to answer it directly. I like it. I like it. So yeah, shortcuts do require some thought, right? So here, I'm not going to use that 1 minus thing. It's not going to help me out at all. Okay, I like it. Any other questions about so far on this?
What's like another question for that? You're not saying at most 6 heads.
I could say it was probably at least 9 heads. How would you get the probability of at least 9? You would add probability of 9, probably 10, 11, 12, 13, 14, and then that's it.
You say something like, I had the question in my head. Like the opposite basically.
Okay. So what have I said? What's the probability of at most 11? So I could just add these together and do 1 minus to get that answer. Because what's at most 11 leave out? These. So I could add these together and do 1 minus to get the answer. Why would I do that in this case? Because it's less work to do that. That's why. So you either answer the question directly, or you figure out the opposite, do 1 minus. So you're answering the question kind of indirectly. When are you going to do the 1 minus thing? When the opposite involves less work. Okay. So when is the opposite thing all true? All the damn time. Always. You can always do the opposite, do 1 minus. Always. But when are you going to do it? There's less work. I like it. Okay. Let's see. Blah, blah, blah. It's connected to the area. So, of course, the shapes here are rectangles. So that's easy. The area of the whole thing, whatever the graph represents, if it's a probability distribution, no matter what shape it takes, the area of the whole thing has to be 1, because it's related to adding up all the probabilities. If I add up all the areas, that's adding up all the probabilities, it better be freaking 1. Okay, maybe. So we have these things, they're called uniform distributions. Let's focus on this for a little bit, because there's a whole couple sections devoted to uniform distributions. That's a word that makes you sound drunk if you're not careful. No, ossifer. It was a distribution. Of course, saying ossifer doesn't help. So something like this, a standard problem would be, have you ever gone to an airport that had a little shuttle that connected the terminals? Yeah. And you just got to love it when you're like, I'm going to make it. Oh, shit. All right. The train takes off. So let's say that train arrival times are train wait times are uniformly distributed. So the times you spend waiting for the train. So you can either get there right when the train gets there, so you spent 0 time. Or you can get there right when the train is leaving, so let's say it takes another, it comes every 15 minutes or so. Right? Or it can come anytime between 0 and 15. So is there any time that's more likely? Well, in our heads, we think it's more likely that we just barely miss it because we pay attention to those times more often, but in reality, it's uniformly distributed. It's an equal probability for any time. So anywhere from 0 up to 15. So it's every 15 minutes. Does everybody understand the basic idea of this problem here? It comes every 15 minutes. So how long could you wait for it? You could get there right when it's leaving, so you got to wait another 15 minutes for the next one, or you can get there right when it gets there, so you waited no minutes. Anything in between is possible. Is any time more likely than the other ones? No. That's what we call uniformly distributed. Uniform meaning everybody gets the same thing. That's where that word comes from, right? Uniform. Everybody gets the same thing. So how tall is this? How tall is this? What did we just say the area of a probability distribution graphed out? What's it got to be? 1. So what height has to be here so that when I find the area of this, it's 1? 1 over 15. The reciprocal, right? So here's how long is this? 15. So this better be 1 over that. So that overall the area is 1. So if it was 0 to 7, the height better be 1/7. If it was 10 to 12, the height better be 1/2. because that's 2. That better be 1/2. So overall the area is 1. It's just the reciprocal, right, to make it 1. Good old algebra coming in again. Finds a way. Because it's useful. Okay, now. So again, I could say blah, blah, blah is uniformly distributed from 11 to 17. So you would do 11, 17, and the height would be 1/6.
Oh.
Now I can ask you any question. Now what's the probability then that you had to wait somewhere between 4 and 9 minutes? The probability that you had to wait between 4 and 9 minutes.
5 times 1.
Yeah, how wide is this rectangle? Representing your question 5. And how tall is it? They're all going to be 1/15. So this would be 5 times 1/15, which is
1/3.
1/3. So 0.3333, just around it. Let me stop there for a second. So this is really a cool idea. I think about again, hopefully everybody knows what I mean when I say dartboard, but it's such a small area, that's why it's given such a high value in a lot of games, because it's so hard to get it there randomly. You actually have to try to get it there with skill most of the time, right? Bless you. So the area of the question you're asking, the area related to the question you're asking, is the probability if the whole thing has an area of 1. It is the probability then.
So if it has less, like, or greater than or equal to, and less than equal to?
No, okay, we're getting into that. We're getting into that. What's the probability here that x equals 2, for example, let's say? What's the probability that you have to wait exactly 2 minutes? This is slightly a trick question, sort of, but not really. What's the probability always going to be related to when I've got the graph here? It's going to be related to the area. So what is the area? The area from 4 to 9 was 5 times 1/15. So what is the area from 2 to 2? No. How wide is this? 0. So the probability that x equals 2, 0. Same way I got 1/3 there. How wide is this? 5. So 5 times 1. How wide is this? If you say 2, then it should be 2 to 4. I'm talking about 2 here. Aren't? The question is 2, not 2 to 4. The question is equals 2. How wide is this? 0. Where does it go from 2? It goes from 2 to 2. I mean, what's the question? Does the question, now here, if I said between 2 and 4, what would that be? That would be 2 times 1/15. So it would be 2/15. Right? So x equal to anything is going to have an area. It's going to have an area of 0. It doesn't have any width to it. Yes?
Something like that, should you put like 0 plus instead, because it's just like that?
Nope. Nope. To be honest, it's a lot more complicated than that. Not that much. Everybody here knows about infinity, right? There's a reciprocal situation in that called iota. Iota is like the reciprocal of infinity in a weird way. So technically, this is 0 because that's the limit of letting it get smaller and smaller. But iota is like, the really stupid way to say it would be the smallest positive number.
Yeah.
If you think about that for a while, it's going to blow your mind. But for the sake of making everything better, for most humans, that would just be 0. I like it. I really want this to it's related to the area. How can something have area if it has no width? So if the probability is the area of the question, and the question has no width, the answer is 0. There's no area. I love you guys. So, what's the area of this thing? 10. What's the area of this? 5. Isn't it getting smaller? And smaller. And smaller. Until I eventually have this. What's the area of this? 0. Yeah. It's got no area. I love you guys. Let me ask you a question that's a little bit easier, but it's still not exactly direct. What's the probability that I have to wait more than 15 minutes? 0. I like it because there ain't nothing out there, right? This is assuming that it's running normally, but we're going to assume that's true. That's what's set up for us. Yes?
For C, did you main put less than X?
Yes, I did.
It's not supposed to be less than or equal to?
Like we just said, this would be the exact same answer. Because equal to 2 has got 0 probability. So if you include it or not, it's the same probability. Yes?
So if you're looking at this, just kind of conceptually, so if you wanted to say, like, okay, the probability that you wait between, like 360 seconds, 361 seconds, and you just switch that to 900 seconds, you could just do that 1 second divided by 900?
Of course.
Okay, cool.
Of course. Yeah, you can subdivide this as much as you want to. Yeah. Yes?
What's the probability under 15? You have to just repeat the opposite. So,
Sorry?
like X less than
X greater than 15?
less.
Oh, now you're asking a new question?
Yeah, yeah.
Okay, so E, the probability that X is less than 15, that would be 100%. I like it. Yes?
The 4 and 9, like, how did you put this 4 and 9 right in there? On like on 0 to 15?
Oh, this was my question here was 4 to 9, like that, right? Yeah. So then I can draw that on my picture. So when I do a problem like this, I'm going to set up the shape, and then I can draw any question. I can draw it in there. In fact, the homework is going to make you do that. Yes?
If you were not waiting between 4 to 9 minutes, like any other option, you could just subtract it. Just go backwards.
So what's the probability that you wait anything other than 4 to 9?
Yeah, like 0 to 4 or 9 to 15.
Oh, no. Then you just figure out the area. That'd be 4/15. That would be 6/15. Huh?
Could you just do 4 to 9 and subtract and go backwards?
Any playing around you want to do, yes, you can. Yeah.
So go back to the idea of the arrow. So like if, with it originally being like the less than or equal to whatever, having it as just less than, we're taking off as such an infinitesimal piece that it just doesn't change the answer.
Okay. I don't want to get too deep into that. I just wanted to bring it up because it kind of came up. If you took any calculus, you used to infinitesimals, which is really what that's related to. You don't have to have calculus to take this class, so don't freak out. Don't freak out. I am going to bring calculus up a couple times just because we're going to use a chart that somebody used calculus, thank God, to figure out for us. So we're like, oh, good. Because one thing calculus is really good for is figuring out the area under things. That's one huge thing you learn in calculus, is given some shape, how to figure out the area. Here, I don't need calculus's help. You're like, that's nice calculus. I can do this shit. But if I start making the top wavy, we're screwed, right? Yeah, and that's where calculus goes, now you need me. Okay. So please don't make a huge deal out of uniform distributions. It really is just finding areas of rectangles. If you're in this area, you're going to have an answer bigger than 0. If the question is outside of that, then it's impossible. This is the only place that it's possible. So what's probably X is less than 0? 0. It's probably X is greater than 0. 1 or 100%. I like it. Okay. So that's one type of what's called a continuous probability distribution. This, hopefully that makes sense, this is a discrete probability distribution. Why do we say that? Because it goes 0, 1, 2. Why is this continuous? Because it takes on every value in between two given values, right? So that's continuous. I like it. Continuous probabilities will always be a little bit freakier because we can't see every single one. Here I can see every single one. Here, in this case, it's not that bad, but still, I can't see every single probability. Okay, I like it. A couple more things about uniform distribution. Let me be a little more general now. So uniform distribution goes from like A to B. Can somebody figure out what the height would be in this case?
1 over A minus B.
1 over
B minus A.
B minus A. And again, the minute you start writing it, generally it looks worse than it really is. All this is saying is, however wide this is, it's got to be 1 over that, so overall the area is 1. Right? Now, who's got an idea of what the mean might be for this? If you rolled a die, which is uniformly distributed, right? A normal non-weighted die. Every side has an equal chance of coming up. What would be the average number you would see if you rolled it 1 billion times? What's the average number that would show up?
They don't come out.
True. So what's the average number you would see? 3. Right? It's the average of 1, 2, 3, 4, 5, 6. Right? Well, 3. Anyway, we'll see. So this, what's the average of this going to be then? A plus B divided by 2. Now, I'm not going to do a lot. There are a couple questions in the homework that reference this. I'm not even going to have this sitting on the formula sheet, to be honest. You have to do the homework. I want you to realize what I said before is true. Anytime I give you a different distribution, there's got to be a way to find the mean and the standard deviation. These are the 2 most important summarizing numbers, right? So sure enough, there is a way to get the standard deviation. And let's see if Jeff remembers this. I don't use it ever. I think it's B minus A squared over 12. Yay! And I actually, I don't know. One semester I had students say, why is it 12? I'm like, it's just the work. No, tell us why it's 12. And I'm like, all right, I'm going to bring the work in. They're like, I wish you had never shown us this. So I could certainly show you why it's 12. If you're curious, I could bring some copies tomorrow. Just lay them on the desk, and you can come up and look at it if you want to. Just somebody remind me. I got some copies of that. If you don't want to look at it, then you just don't come to the desk and look at it. I mean, it's that simple. I don't have any suggestion for eye bleach after that if you want. So, I mean, these 2, you will use them in the homework. They are just stupid little formulas that you plug those. So what would the mean of this one be?
15 over 2.
15 divided by 2, 7.5. And the standard deviation, you just plug the 15 squared divided by 12 squared, whatever the shit that is. It's just a formula to plug stuff into. You with me? But I just want you to realize there's always a way to get the mean and the standard deviation. These are not that important, but I want you to be aware that they exist. Okay? Okay. Ooh, so the last thing for today, obviously. We've already talked about this several times. So the normal distribution, what's it look like? Do it in the air. Ooh, I like it. Not a nifty shit.
Oh, it's okay.
Normal distribution. Yeah, some of you guys are. Don't do that one, Jim. So it's like that. Wow. Okay. This is also called a Gaussian distribution, Gaussian curve. It's used for other things besides this, to be honest, but.
Is that named after
Gauss, yeah. Gauss did way too much. Yeah, he had so much time in his hand. I don't know. He was just too much. Like, break this guy up and make 3 people out of him. But you see the name Gauss everywhere. Like, magnetic field strength is in Gauss. It's crazy. Yeah, dude. All right. Considering what we just talked about, will questions about probabilities for this be this easy? So if I knew the mean height was 68 inches, and I asked was probably that somebody said more than 71 inches tall, can you find that area? You can? Show me how. Do it.
Calculus.
Now, even with calculus, the formula for this, I can't remember if they put it in this book. Give me a second. You guys are all antsy. We're like, here. Yeah, here we go. All right, you ready? You're not ready. There's the formula for that curve.
Can you make it clearer?
Wait a second. There we go. It's a little bit better.
You don't have to know that.
No. Some of you guys might notice, do you notice if you know any calculus, see how it's e to the x squared basically?
Yeah.
And that's that's your most basic example of when you can't do the integral by hand. You have to get a series. So, and if you don't have a clue about again, you don't need to know calculus, to know statistics. You understand? And right now, just realize we're never going to use this sucker directly. But if you plug this in your calculator and put a value for mu and a value for sigma in your calculator, it will graph this. This shape will happen. That is the function whose graph looks like this. So everybody in here should be able to understand what I just said. You put that in the calculator, in your graphing calculator, it will graph a shape like this based on what your mu and your sigma is. So, in order to get the areas, we're going to need some help. And thankfully, like I said, I think next time I'm going to give this to you. We have a chart that's got all the areas based on how far away from the mean you are, done for us, that used calculus to figure them out. So we'll look at that next time. I think that's plenty for today. So tomorrow we got that quiz first thing. And then we'll keep going with chapter 6 and chapter 7. Look at the crazy people we are.